There are plenty of cases where people say, no, I don't have any flexibility on this. You're like, yep, okay, I get it. We're going to use Inconel 718 and it's going to be exactly by the book. Where you are in a position of authority and you've got some flexibility, most people get the best business case when they're able to say, well, the intent of this coating is really wear resistance.
Right.
Printed that hub up in cobalt, which is a very wear resistant material. And then we've printed each of these blades, and then we've finished some and left some as printed so you can see the difference.
Wow.
But we do all of this work. If we had machined this from solid, it probably would have taken close to 24 hours to complete. Doing it this way is about 3 hours, 3 or 4 hours.
Manufacturing Insiders. Today I have an exciting guest with me, Jason Jones. He is a PhD, very well educated man. He is very passionate about additive manufacturing and 3D printing and just overall the future of manufacturing. So welcome to Manufacturing Insiders, Jason.
Thank you, Nate. Great to be with you.
Awesome. So in your mind, what does the machine shop of 2035 look like to you?
Well, in some ways, I might have had a preview of this already, and I'll tell you an experience I had, just a quick one. I was able to visit Fanuc, which is a Japanese robotic leader.
Yep.
And as we arrived to the factory tour, there was nobody there. It was crazy. There was this massive factory, and we were wandering around, almost felt like it was after hours, but it was the middle of the day. And there were very few people managing a whole flood of a fleet, I should say, of robots doing lots and lots of parts. It looks like a flood of parts coming out of the other end of the manufacturing facility. It was just kind of a fun little, maybe this is what it'll be like.
Yeah.
I don't think it will be devoid of people at all, but it was like an eerie feeling that I think people that see manufacturing in the future could also feel a lot being done under its own intelligence.
Right. So what does your product, your invention, what part does that play in that future?
Largely, it brings together what has been siloed different activities. And so manufacturing is such a rich tapestry of different processes. And right now, most of the time, a part gets advanced from one process to the next. If it's made in the hundreds of thousands or millions, it might be on an assembly line and it moves through automatically. But for the vast majority of parts that are not made in such high volumes, there's an individual person moving that along or moving it onto a conveyor or moving it, right? There's a lot of moving going on by operators and individuals still. And we kind of invert the rules on an assembly line. Instead of moving a part between different machines, we essentially move all the processes to come and converge on a single part. And it allows you kind of that same level of flexibility, but with a far lower investment.
And I mean, that sounds awesome. And it sounds, like it'd be a huge advantage to a lot of companies to incorporate. So in simple terms, what you're doing is you're allowing for the combination of, additive manufacturing with the traditional subtractive all in one machine.
Correct. And in addition to that, there are some inspection steps that can be really useful that may not be as familiar to a typical machine shop. But when you start to add metal, they become very, very useful.
Right.
Or polymer composites.
So for those in the audience that might be a little less educated on the subject, can you just define additive manufacturing, maybe in the broad context, but then more specifically in the context of what you do?
Absolutely. So in general, most people are familiar with machining, where you take a solid block of material and you remove essentially what becomes waste and you leave the part after you're done. When you do additive, you start the opposite way. You start with usually some sort of substrate or maybe a round tube or a bar, and then you build onto it. So your final part is always larger than the starting point.
Right. Right. So with additive, you're building material onto that, and you can do that with multiple materials. You can do that with metal. You can do that with plastics. Can your solution do both?
Correct. Yes, it'll do both. And people are always like, well, what's the range of materials? The short version is if you can weld it as a metal, you can probably 3D print it if you get the right setup. Mm-hmm. Also, from a polymer perspective, we're focused on thermoplastics. We do not do thermosets. That's a different set of technologies.
Right.
If it's a thermoplastic and it's used in injection molding, there's a high likelihood we can print it. Depending on the shape and geometry, it may or may not make the most sense to do it.
Right.
But that's kind of, it's a very wide range of materials.
So, you've gotten into this extremely, niche specific technical aspect of manufacturing. What's kind of the path you took to get there?
So I got involved in 3D printing decades ago.
Okay.
It was quite early in its iteration. And at the time, and maybe I should pause, 3D printing is an umbrella term for like, right now there's 7 standardized families, right, that have common sets of physics. I got involved as the 7th family had recently been kind of identified. And everybody was saying the first 7 are great, but what's that 8th category that's going to do everything? And of course, the real answer is, as is always the case in manufacturing, no single tool or process is good at everything.
Right.
And so, although we sought, and actually for 7 years, I was dedicated professionally to try and find that 8th category, and we certainly made some great discoveries, and there are a number of technologies that have come out of that and been commercialized. But what the real sort of key understanding is, you actually need this suite of different processes to get to the interesting things that everybody wants to design and make. And so if you have to have 4 or 5 or 6 or 7 or 8 technologies, why can't we make them intermingle and have them digitally change in and out? And then you've really got something interesting on your hands.
So when you're talking about integrating all these technologies, what does it take for a manufacturer? I mean, it sounds very interesting. I'm sure a lot of machine shops out there might be like, yeah, I mean, we could certainly use this. Like, what does it take to do it? Can we retrofit this? Can we, is it a separate machine? How does it work?
So we originally intended to say, hey, let's find some machine tool builders and they'll integrate our equipment from the beginning. We struggled to find them.
Sure.
So we actually said, okay, fine, we'll launch as a retrofit solution, which is what we originally designed, is this ability to add on to an existing CNC machine, the ability to 3D print polymer composites or metal.
Right.
And after we did that, then the OEMs, the original machine tool builders were like, this is actually a great idea. So we started with Hamel and then Mazak and then on through a long list of machine tool builders. So you can get it either way. A lot of people start by dipping their toe in the water and they're like, hey, I just want to try this one part and I've got an old machine in the back. Can you make that work? And often we can. And then frequently that generates enough confidence that then they want to go buy a new machine, a hybrid machine, right? Fully designed from the beginning as a hybrid process.
I see. Yeah, that's an interesting concept. And it's one that I've had recently with a couple people about, you have a great product idea and there's a lot of these big Fortune 500 OEMs that should be using your idea, but you can't really get their product teams to accept it, or their science teams or whatever it might be. And what we discussed was that really the key to doing that is to make it as easy to integrate with their current process as possible. And so I think it's an important point you brought up there.
There's so much inertia around all of manufacturing, right? It requires specialist skills, specialist equipment, that unless you do something that's not just a little better, it's got to be dramatically better. And you need to be able to demonstrate it.
Right.
Is at least my experience where people are like, oh, okay, I can see why this is a winner and we need to transition.
Right. So how many people out there are doing, making hybrid machines or hybrid machine technologies like this?
So there's probably about 24 companies that claim they have some kind of a hybrid offering. We have helped enable about half of them to develop at least the beginnings of their hybrid solutions.
Okay.
And maybe that gives you a little context.
Yeah, that does. And so you're really working with all the big players. Mazak, Fanuc, who else is out there? You got the German Rhodes?
Yeah, so the way we've done it is we've tried to partner with machine tool builders that are across the spectrum, trying to kind of fill it in. So about half of our equipment ends up on a Haas machine simply because of its prevalence in the market.
Yep.
We also like Herco. They've got a very unique control. And so there's people who are like, no, I want to do it on this. We then went on to Hamel and George Fisher and Mitsui Seiki's at the very high end in terms of very precise parts, right? They make 80% of the world's aerospace grade ball screws on their machines. And so you have this spectrum, even grinding companies, right? Like Elb and others. It's like this solution has the potential to address the right sets of products and do it in the most cost effective way that people are seeing.
So you just mentioned grinding. So are there more functions of this technology beyond just the additive and I guess the typical machine tool? Like, is there a grinding function? Is there some of that finishing stuff?
Yeah, when we talk about hybrid manufacturing, some people in the market have already seen this idea of doing a little bit of printing with finishing, like with machining, right? Seems usually milling. That's a great combo to start with. But our definition of hybrid manufacturing really anticipates a very rich uh, landscape of different solutions that are suited to different parts. So when you talk about 3D printing, the first thing you really need to talk about is materials, because that determines what type of 3D printing you're going to be doing. And B, usually the stiffness and rigidity of any type of finishing equipment that you need to use to get it finished. So as you get into the nickel-based superalloys and cobalts and other things, as it gets harder and harder and harder, or more and more and more dense, often then you look toward a higher-end machine tool and or grinding.
Okay. So can you tell me, just so I can picture this a little bit better, can you tell me a story of a significant problem that you've solved? Somebody came to you and said, hey, we want to make this part with hybrid manufacturing. And how did you help them out?
Sure. So when you say significant problems, they take a couple different shapes. But at kind of the simple end, we have a lot of people. In fact, one of our customers is a plating company, and they specialize in chrome plating. Well, especially in Europe, but also to a lesser degree here in North America, we are seeing a lot more regulation, a lot of pressure trying to get rid of the chemicals that are involved in hard chrome plating. And so the question is, hey, can you provide a coating onto parts that will be a substitute for hard chrome plating? And the answer is yes. We can use a laser beam and metal powder and create a fine coating that's usually a little thicker than what you would get in a typical chrome plating process. But the ability to do wear resistance and often even the corrosion capability far exceeds some of the chrome coatings that are available now. And so when you say, hey, what's a big problem? Well, corrosion is a massive problem, right? It's a many-fold billion-dollar problem that the whole world deals with. Now you've got an alternative solution that's economically more friendly. And from a cost perspective, if you look at just the coverage moment, chrome plating may be a little cheaper, but if you look at all the labor involved in masking stuff off and getting it prepped, this is a digitally driven process. So you literally spray it down where you want it, and you don't where you don't need it. So if you look at that whole workflow, you're very cost competitive, often more cost competitive than typical.
And obviously you don't have to ship it to that third party and all of that. Yeah, I mean, I would imagine like at face value, you can do a batch of parts with hard chrome all at once, but getting all of them into the bath and then transferring them out and everything else you have to do in between, even though you might not be doing as many parts at one time, you probably end up being much quicker on a machine.
And for a lot of people, it's about trying to shorten that turnaround time, right? Lots of industries are really based, the quality is fixed, right? The threshold at least is fixed. You have to meet this quality. How do you differentiate? Turnaround time. And if you can pull a process in-house that typically would be something you send out, even if it's a great relationship, right, with that subcontractor, it just gives you more flexibility to prioritize and move things around and do it, just turn it around.
Yeah, and you said basically any materials you could weld, you could do here. And I'm not aware of that total data set. So, if we just think about like some of the common coatings that someone might put on a part after it's done, whether it be, you've got your anodizing, you've got your electroplating, you've got your, some of those materials that they put on molds to, help the parts release.
Sure.
How many of those could you address with this sort of a solution?
So, one question we need to start off with, and this is important for anybody who's looking to 3D print stuff, right, and use parts, is do you have the authority to make any changes
Mm,
to A, the composition of what you're putting down,
right,
or B, to the design?
right.
And there are plenty of cases where people say, no, I don't have any flexibility on this. You're like, yep, okay, I get it. We're going to use Inconel 718 and it's going to be exactly by the book. Where you are in a position of authority and you've got some flexibility,
Hmm.
most people get the best business case when they're able to say, well, the intent of this coating is really wear resistance,
Right.
but I can use an alternative material. Most people, so many people are like, well, I'm going to make this part and harden it. And it's out of D2 steel, right? Tool steel. And they get a very hard part. But we've got, in fact, an entire automotive assembly line here in North America where they've transitioned from doing fully hardened tools to having what they call a relatively soft steel underneath and just a hard shell printed on the outside.
Mm,
Well, why would they do that? And the answer is, as they go through this, it's a stamping die sort of progression on steel panels for a car. As those dies get some damage or they're misaligned by poor setup or something like that, if it's a fully hardened die, they've got to take it off. They have to go get a replacement. It's a long-winded replacement process, right?
yep.
Whereas right now they have a hybrid machine that sits alongside that line.
Right.
They can literally pull it off. They usually have it fixed in 30 to 40 minutes. They can have that line back up running in an hour.
Wow.
Now,
Yeah.
some people have a whole second, a second set of dies, which is also understandable, but the investment in that second set of dies is often millions of dollars.
Wow.
And so for, less than that, a fraction of that, you can have a machine now that allows you this flexibility of saying, I'm going to repair on demand whatever we need and not have to have all that cost tied up sitting around.
That's phenomenal. Yeah, and I mean, there's a whole kind of range of implications for die repair, even beyond, making the die with the hardened coating, but, being able to do the kind of electroplating buildup and then to simultaneously almost grind that back to, make that die the original spec, right?
That's right. Yep. And we see plenty of people who will start off and maybe in an injection mold context. They're like, hey, this is a mold we're using. We set up the gate at this size. And then as they get into it, they're like, actually, we need to make a little bit of modification.
Yep.
Well, you can always cut more off. But if you need to add more back on, that's where we come in. You
Got
can actually add metal back on, then finish it all and blend it in. And you don't, you haven't lost it. You don't have to make a whole new one from scratch.
Okay. So in those injection mold dies are a good example of when they're wanting some sort of lubricity to it, which normally includes some sort of a Teflon based material or something to that effect. Is there something that you can accomplish that with?
So there are release agents that get sprayed onto a mold.
Okay, yeah,
We don't do anything with those, right? What
sure,
we do is provide a base metal that gets shaped, and then whatever you want to spray on, you spray on.
right.
There are other cases where the base metal does want to change. And a good example of that is in the glass bottle mold
Yep,
making industry.
yep,
The rate at which they can get glass bottles out of a mold is determined by how quickly the heat gets pulled out of that glass.
correct.
And
So
there's
they make them out of brass, right?
they do, they have a lot of
Yeah,
bronze molds.
bronze.
So there's
Right,
Yeah, glass in its molten state is quite abrasive. And
right.
so the default material for decades has been cast iron and it holds up reasonably well. And at the edges, which is where most of the damage happens, many times glass bottle molds get a replacement edge and it ends up being a nickel-based alloy
Okay.
because it's easier to repair and it's stronger and tougher and for all those reasons. So we actually have a fantastic customer that said, we want to apply this to glass bottles with bronze as the base material because it pulls the heat out quickly and gives you a really nice finish on the glass. And then we use the laser printing process or the laser deposition process to be able to print those edges up
Hmm.
as reinforced edges. And
Interesting.
it allows them to achieve all of this workflow in a much simpler setup.
Wow, that's fascinating. So somebody has a machine shop and they're listening to this. How do they know if they should be the ones that should be looking at this technology, whether it be from a price point standpoint or whether they're even manufacturing the right parts to even care about it?
So the solution we provide addresses three or four things, right? Three or four difficulties. One of the difficulties is, do I have like a wear problem where I'm trying to address a part that's wearing away? Anytime you're in a workflow where it's like, hey, should we weld this up manually? This becomes a really good candidate for that. A lot of people talk about themselves as remanufacturers when they're in that workflow, right? If you're grinding something down as weld prep, if you're having to manually weld something back up and then go back and finish it, you're already accustomed to these same ideas. This is
Right.
an automation solution for you,
Right. Yeah.
right? Likewise, if you're saying, I think that we're constrained because I'm trying to get one material to do everything, this is an alternative for you where it's like, we may not have to do a fully hardened part, right? Most of the wear happens on this edge over here or this corner right there. We've got various people who allow 3D printed material. And when we 3D print material, we can do a little bit of mixing and matching.
Mm-hmm.
One material that's really neat is called a metal matrix composite. People say MMC for short. It's basically like a Rice Krispie treat in how it gets printed. What
Mm-hmm.
happens is the Rice Krispies end up being particles of ceramic, and it could be tungsten carbide or some other very hard material, or maybe some other type of abrasion resistant material.
Yep.
The marshmallow holding it all together. The beauty of that is a lot of these hard materials, if you strike them and they get a crack in them, frequently that crack will propagate all the way through and you have pieces cracking off,
Yep.
right? This goes for agricultural equipment or forestry equipment or something like that. If instead we use this kind of Rice Krispie treat approach, where it's a mixture of metal that doesn't propagate cracks embedded with ceramic particles, then what you find is something comes into contact with it, you wear, right? The wear resistance comes from those particles. But if you suddenly get a strike from something that's hard, let's say there's, metal inside of something or ice or rocks or something else embedded in wood or whatever you happen to be rubbing up against, it doesn't crack the whole thing to pieces.
Mm.
You just you lose a little bit out of it, but you still have the rest of that metal holding all those particles in place. You get a much higher toughness as a result.
Very interesting. Yeah, it's a some of these innovative materials, they're really fascinating. I actually have a podcast coming up. I did the pre-interview with another doctor. Um, his name is Pritam Poddard, but he was familiar with your technology because
Mm.
what he's doing is developing it's essentially a structure that's 3D printed that replaces the typical honeycomb structure of like it would be a satellite or an aerospace component.
Sure.
And his technology is evidently allowing you to produce very large pieces because on a typical 3D printer you have pretty big size limitations, but then
Sure.
also the actual structure of this is kind of like I'm trying to think of what it would look like, but
Like a
instead of
lattice or something
a
else, maybe.
lattice, exactly, that's the word I was looking for. Yeah, very, very cool stuff.
The whole world of lattices is a fascinating world. It's for us, since we deal a lot with machine shops, they don't typically, love lattices. They don't know how to produce lattices. It's not normally in their wheelhouse.
Right.
Some types of 3D printing certainly allow that, and it's amazing the amount of stiffness you can get, especially to weight ratio,
Yep.
as you look toward lattices.
Yep. Yep. So beyond, maybe somebody, it sounds like if you're in the tool and die space or in the tool and die repair space, this is probably a no-brainer for you to incorporate hybrid manufacturing. Can you think of like another, I'm sure you can you mention to me another good use case that is sort of a no-brainer? Like absolutely this type of company should be using our solution.
Sure. I worked at a machine shop, right? That's partly why I have an intuition for this. I happen to be in a prototype machine shop.
Yep.
So we didn't do large volumes,
Yep.
but I would estimate I probably spent, and the team collectively, we probably spent 30% of our time figuring out how to hold complicated parts.
Mm.
Well, if I suddenly have the ability to 3D print, then I can do a couple of things. I can print unique, either soft jaws or other types of jigs and fixtures that could even be sacrificial. I don't have to print it out of metal. I could print it out of a polymer composite that prints very quickly, but that's at scale, right? You talked earlier about size limitations. For us, when we add equipment to a machine tool, you can then use the full travel of that machine tool to deposit material on.
Right.
It doesn't always work out that somebody's like, well, I'm going to grow a part from scratch that's the full volume of my CNC bed. We got to look at the economics for that to know if that makes any sense. But at least you've got no inherent size limitations, right? But being able to look at jigs and fixtures and other things that are aids to manufacturing a final part, that's a real winning application for many of these. So if you can reduce that 30%, even just down to 28 or 27 or 26%, suddenly you've got a 4 or 5% increase in your output.
Yeah. Yeah. So absolutely fixturing. And you have obviously multiple axes you can work on with a lot of these machines, and with a traditional 3D printer, you typically, which I'm not really that familiar with the world of like high-end 3D printers that cost, a couple $100,000. I don't know what they look like, but what's kind of the comparison between using this on a typical CNC machine, maybe a 5-axis CNC machine versus a common high-end 3D printer?
So I think it's important to kind of think about the origin space of 3D printing. Early on, and this goes back decades, when 3D printing was invented, it could do very complicated geometry, like more complicated than any other manufacturing process, which is partly what it's known for, right? You've rarely seen some of these lattice structures, or if you need to print a simulation of a skeleton, right? Frequently inside a bone, you got varying densities and even, little struts and things that interconnect in a very organic shape. Yeah. We're not used to making that typically on a machine tool. So on a machine tool, you can get the outside very complicated. And I love at the shows when people have done really complicated, detailed work. It's fantastic. But as a general rule, we're not accustomed to organic shapes that have got a lot of, especially internal complexity or unusual surface textures. 3D printing is really good at that. And the early properties of some of those 3D printed materials were not fantastic. It wasn't as good as injection molding. It wasn't as good as a cast part, that sort of thing. Yep. And as a result, it ended up becoming a development tool. It really started, and it's first, in fact, we call it rapid prototyping for a long time. Sure. Because it was used for making prototypes. Right. Well, how robust is your prototype? Well, you can get the size and form right, but then if you drop it, it shatters into a million pieces. That was really the original large-scale use case. And it remains to this day a super critical thing. If you're not using 3D printing to get prototypes ready, I would seriously evaluate that. Right. Then, as the materials have gotten better, it's suddenly like, oh, I can start to print more and more. But the mindset of print from scratch still remains that if I'm going to print layer on layer on layer, if you think about a ziggurat pyramid that's got stair stepping along the outside of it, yep. The idea with 3D printing was, and in fact, one of my favorite printers said, well, you can print this in high speed mode or high quality mode. What was the difference? The difference, of course, was time, but it was largely about how tall each layer was. So high speed mode made it look like the steps were much larger. We call it a stair step effect along non-vertical walls. You get that.
Like pixels on it, yeah.
Exactly. It's pixelated, but in a three-dimensional sense. And then the high speed mode, the high quality mode would half the layer thickness. Right. So your stair steps were much smaller. And yes, it was closer to the shape you were really modeled in CAD.
Like integration, actually. Back to the engineering background.
Absolutely. Yeah. So that was a trade-off. And I'm like, I don't want to have the trade-off. Right. And as we looked at this, part of the reason we said 3D printing belongs inside of a CNC machine is that you can print it essentially in high-speed mode, so long as you're getting the internal properties you want, the microstructure you want for your metal or polymer, print it as fast as you possibly can. Because CNC machining is so mature and so well developed, we can smooth out those outside surfaces much, much faster. Right. Than trying to couple the two things together that are coupled largely for historical reasons. And that's really what this hybrid manufacturing approach allows you to do. Decouple those two, print it as fast as you can, come back and finish the surfaces however you'd like. Finish some surfaces really well, others you can leave as printed, and maybe there's an intermediate place as well where you're like, hey, I'm just going to go over this quickly, and it may be scalloped, but it doesn't matter for the sake of the part.
So to give kind of like a my understanding level summary of what you just said, essentially the coupling of finishing with the printing is really the big deliverable, with this hybrid manufacturing.
For sure. And it's partly this flexibility that allows you then to choose, just like in milling, where you can choose, let's say you have a ball end mill and a curved surface, you can choose what your step over is and determine your surface finish based on the application need. There's less flexibility in 3D printing with the stepping up. Typically, you usually have one or two choices, not this infinite range you get in machining.
Yep.
And as a result, you end up sometimes taking longer to print than you need to.
Yep.
And you still have to finish it if you need the precision.
Yep.
And so why not combine these two? And in fact, I can show you a quick video if you just want an idea.
Yeah, absolutely.
Together for those. Perfect. And for those listening along, I'll voice over a little what's going on.
Okay.
So what I'm going to show is a video. It's about a minute long. And what will be displayed is the loading of a metal deposition head. This is a head that we call directed energy deposition. That's a particular style of 3D printing, and it's just automated welding using a feedstock that's metal powder in the case of this video.
Okay.
And then it's going to melt onto the edges of a tooling insert. It's an insert where the edges are that's the weak point. That's where it wears out.
Right.
We're going to print reinforcement all the way around the edge. Then we'll transition to a cutting tool where we finish the 3D printed area, because when you print something, you often end up with a texture like sandpaper. It's not necessarily smooth,
right?
But it's not just going to finish it, it's going to blend it into the part beneath. So essentially you've left your machining allowance on and then you pass all of it together. So it's perfectly blended. Then we're going to introduce a head that actually is called an eddy current inspection head. And it will then look at that metal that was just printed and finished and make sure that it doesn't have any cracks in it or any substantial voids near the surface.
Yep. Okay.
So here goes the video. So here you see the loading of that deposition head. You have a supply unit that comes down to connects to it.
Okay.
Now this is a laser melting that metal powder just as it arrives to the surface. And in the as printed state, again, it's pretty rough. So now we've switched over to a cutting tool and you can see us cutting along, and you actually see now this is two metals in one part. Some people call this a bimetal part. And what we printed around those edges is super tough and super resilient. We've now switched to the inspection head to check to make sure that that tough, resilient material has been printed well. And it gives you feedback to say it's good or it's not good. But that material we've used at the edges, it's expensive enough you'd never justify printing the whole part out of it. But it makes perfect sense, especially if you can take the base material you've made that part out of and make it a low-cost material, right, which in this case is certainly, right, this is cast iron. It's about as low cost as you can get.
Right. And
then we printed an exotic material on the top. Usually the blend of those two gives you better performance at a considerably lower cost.
Interesting. So time-wise, what I just watched there, was that real time? Like that's how long it took to...
So that was chopped out. I think that was an 8 or 9 minute sequence.
Okay.
To print all the way around the edges, multiple layers,
yep,
finish it all and inspect it.
Yep.
So it's still sub 10 minutes. You just watched the chopped up version, which is why it's only a minute long.
Right.
But the motion you observed is real time.
Right.
So it's not uncommon for you to be machining it, machining at 20 or 30 inches a minute, maybe faster. You can also print often around those same speeds.
Wow.
And it's just the size you're depositing as you go.
Because there's guys out there that are hand welding, build up,
yep,
loading into the machine, grinding it, getting it to fit the original mold, taking it out, inspecting it. I mean, that's got to take several hours.
It does. And if you do it once a year, keep you doing it that way.
Right.
But if you do it once a week, you should consider an automation solution.
Right.
And that inspection step that you saw at the very end, there are workflows, especially in the remanufacturing world, where you get a part in, you need to inspect it before you weld it.
Right.
You actually need to inspect it before you do any weld prep, which is usually grinding, right?
Yep.
But if I can now, and then you need to inspect it again after you've done the weld prep grinding.
Right.
And then you need to inspect it again after you've welded. Well, that's 3 times that part's got to go on and off that machine at least. Sometimes it's 4 or 5, depending
Cow.
on the
Yeah.
features. If I can now pull this in as an automated sequence, and I can do the inspection fully automated in a couple of minutes,
Yeah.
all of a sudden you take out all those setups, all that moving around, and it just gets consolidated into one spot. That's why I refer to this as kind of the inversion of an assembly line. The
Right.
part doesn't move along, right? The part stays put, but all these tools come to it, and you're able then to, in the case of a weld style repair, you can inspect it, make sure it's good. Then you can do the weld or grinding or weld prep milling, typically in process. Then build it up, then finish it, then inspect it again, all as a complete cycle.
Wow. Wow. So yeah, and you could almost picture, you could buy one of these machines. Like, I talk to a lot of guys that are just starting a machine shop, and yeah, I got a 3-axis machine. Hopefully I can afford a 5-axis in a couple of years, whatever. And so then I got to go out and try to find some overflow work to fill their 3-axis. You can almost picture somebody buying one of your machines, right? And building an entire business around it. I mean, even if you were just to focus on low cost, fast turnaround mold repair, I mean, you could probably pump this stuff out, and make a margin on stuff that would, be saving them 50% on what they were paying for.
Where you have complex workflow, right? Job shop type stuff where stuff's going on and off and on and off and getting rerouted all around. This does represent a step change in how you can often consolidate steps.
Mm-hmm.
So I will mention about 80% of our products end up in a machine that does at least have a 4th axis. Okay. It's 4 or 5 axis. Yep. Because as you're printing, you want to be able to rotate parts around. And in fact, I'll just show on screen. This is a part right here that it's a rotor that's intended to be used in a generator. And this is a style of generator that's actually used downhole in the oil and gas industry.
Okay.
And so to rotate this rotor, they're actually flowing the slurry past it.
Okay.
That slurry is very abrasive. And so these fins that you're seeing on screen, they will wear away, and they'll wear away quickly depending on the material they're made from.
Right.
As a result, what you see is a shaft in my hand that is steel. But then we've printed up this entire hub. If you look at the back of that, you can see these layer lines.
Yep.
We've printed that hub up in cobalt, which is a very wear-resistant material. And then we've printed each of these blades, and then we've finished some and left some as printed so you can see the difference.
Wow.
But we do all of this work. If we had machined this from solid, it probably would have taken close to 24 hours to complete. Doing it this way is about 3 hours, 3 or 4 hours, something like that. So it's a much shorter path in a material that's really hard to shape, but it gets you to the finish, place much faster. But you can see why we want the rotary or sometimes 5-axis solution on there.
Wow. What's the biggest limitation you have? I mean, because I'm thinking to myself, if I had a machine shop, man, I would be doing this. Like, what's the biggest limitation you have? Why? I guess what do you see your current adoption level at, and where would you like it to be, and why isn't it there yet?
So I would say imagination, and then the perception of standards. And I'll clarify both. Imagination is mostly because people haven't quite realized that this is so practical.
Mm-hmm.
And once they do, then it's like, oh, I get it. The other is there are some very legitimate reasons why the standards don't allow us to quickly change material types or
right.
geometry.
Right.
And the more safety critical an application or a part, right, they're there for a good reason.
Right.
That said, the perception of it'll never get approved or it's so hard or there's so much inertia around that sometimes steers people away from material sets that actually have quite a lot of data behind them that will perform much better.
I see.
The video I just showed you a minute ago that has that deposition around the outside of that tooling insert.
Yep.
We love that environment because normally the products are heavily regulated, or often they are, but the tooling itself, as long as it performs well, there's not an external regulation for it. I realize if you're a tool maker, you've got to guarantee your work.
Right.
But it allows you to assume some of that risk. And so it's an easier place to adopt.
Very
The
interesting.
same is true in, often agricultural equipment. If you're working on a combine or something that's used in forestry or something that's in mining, usually the regulations are lower. We do have equipment and parts that have been made using our equipment that are flying on aircraft. And it was a larger effort to be able to get that fully approved, which it
Right.
is fully approved for certain designs and certain materials,
Right.
but it's not the sort of task I would recommend a small machine shop take on.
Mm.
That's really more of a tier one or OEM scale of activity where they're trying to get something requalified. Does that
Gotcha.
make sense?
Yeah,
So I
absolutely.
try to, yes, the potential is amazing. Yes, I believe this technology will be in the vast majority of machine shops across the US and the world. And yes, right now we're in still an early, we're probably moving into an early majority phase. We're probably on the edge of early adopter or early majority sort of uptake where people are like, okay, this is my workflow. I see that hybrid manufacturing is going to automate much or all of that and
Yep.
get me out those parts on the other end. Makes total sense.
Yep.
So, building some people's idea is I'm going to build a part from scratch because it's 3D printing. Our view is most of the business cases, the low hanging fruit, they still involve adding a little bit of metal to an existing part. Okay. With polymer, you've got a lot more latitude on that. There's a lot more freedom in terms of cost and time to build from scratch. But for metal, we still see some of the best business cases from adding 5% or 3% or maybe 10% onto a part, but not necessarily growing everything from scratch.
That makes a lot of sense. Yeah, and so it almost seems like, it's kind of an engineering adoption problem. The guy that's making the specifications for a part needs to be more aware of what hybrid manufacturing can do so he can specify and give the company the latitude to do that.
You're right. And typically, where it's like, hey, this thing wears out, you can often replace a surface coating with very little sign off,
Right.
right?
Yep.
And so when you said to me, hey, where's the adoption? That's why I start at coatings and repair. By definition, if you're repairing it, you have the option to improve its performance, right? You're going to
Right.
restore it to the same shape,
Right.
but yeah, you're going to give it a different coating. So coatings, repair, then adding and building up features like the example I just showed you. And then
Hmm.
I'll just show you a last one. This is a part that's been printed from scratch. This is polymer composite, so it's got carbon fiber in it. It's a
Okay.
very stiff, lightweight structure, never rusts. This
Okay.
is the kind of material that we see people doing jigs and fixtures in,
Okay.
right?
Yeah.
So, and even inspection fixtures and other things. So I've got another thing on here. You can see this piece of metal is held into a polymer composite fixture
Yep.
for machining at an angle so that if you are that guy with a 3-axis machine and you got to get off axis somehow, right,
Yeah.
out of that sort of Cartesian set, you could print this rapidly and then put it at a different angle.
Very interesting. Yeah. Yeah, I actually just was talking to a company. He actually was on the podcast too, but they do custom motorcycle builds. They have their own line of motorcycles they build. Really awesome. It's called Combat Motors. But he said that the one thing they were kind of looking for was somebody to make carbon parts, like I think the fender, maybe some of the different cosmetic parts. They like that kind of carbon look to them.
Sure.
So depending on how big these parts are, which I didn't get the impression they were super big, it seems like you could probably make these parts with one of your machines.
Absolutely.
That's cool.
If it fits inside your machine tool, it's worth looking at.
Do you do any actual contract manufacturing yourself?
We do. Yeah.
Yeah.
Anytime somebody is like, hey, I'm really interested, frequently the first thing we'll do is say, well, let's see if we can get a part made for you.
Yeah.
And so for both our comfort and theirs, right? We want people to derive value from what they're doing. We'll look at it. If it doesn't make sense, we will tell you, go use a different 3D printing process or stay with machining. If that's clear to us, we will tell you.
Hmm.
If we think it does provide value, then we'll also say, and there's some gray area, then let's say, let's try it, see where we get to.
Interesting. Yeah, I'll have to make an introduction with that guy, because I don't know that he's found somebody. But I always like to wrap up my podcast, which actually I'll get to that in a minute. What was I gonna? Well, I might as well ask it now because I can't remember what my original question was. But when you're kind of looking at your business from a business development standpoint, a resource standpoint, employees, all the common troubles manufacturers are having, are there any things that you've been looking for? Any resources that if somebody was listening, hey, I'd like to talk to?
So from our perspective, we're always looking for what we regard as early adopters, right? Or earlier adopters. Because of the principles that are in place and the savings that comes, I'm confident this will spread ultimately across, right, most machine shops.
I agree.
But we're very interested to find those people who have a little bit more risk tolerance and who are hungry to try something that could really help them stand out.
Yep.
That's probably what we seek the most, is people to partner with, to work together on.
Absolutely.
And we try to make that a true partnership. And I'm pleased to report we've got good relations with all of our people that have purchased systems. To my awareness, we haven't fallen out with anybody and said you're gone. But that's because we know when you buy capital equipment, especially, you're making a partnership with somebody to
Right.
help them more money.
Right. Yeah, there was a couple other questions I wanted to ask around that. So somebody buys one of your machines or retrofits one of their machines to use your retrofit solution.
Yep.
What's kind of what changes about their marketing strategy? Like, how do they advertise their new capabilities to the marketplace?
The people that do it most successfully have an application space where this provides them benefit, and often they don't say anything about it. It simply allows them to deliver a higher quality, longer lasting process or part.
Right.
I mentioned earlier I showed you the video of that little tooling insert. By putting that edge around, it triples, it's somewhere between tripling and quadrupling its lifetime for an incremental about 10% of cost.
Wow.
So if you're already building that part and it's X amount, right? For an extra 10%, you can build one that's triple the lifetime. It's an absolute no-brainer.
Right.
And then if you go out to the market, people will often put sort of code names on it and like, this is the new blah, 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 blah. They'll sell it for an extra 40, 50%, and they'll guarantee it for twice the life, right? Then you're at that sort of point where people who are already are like, ooh, this has worn out kind of quickly. Let's try the next version up.
Yeah.
And they often don't say that it's 3D printed.
Right.
And for me, as long as it meets that application, it's fantastic. I love 3D printing, right? I also love machining. But 3D printing in particular has kind of captured people's imagination such that there is a mix of hype and reality in circulation even after decades. And so to me, where you simply deliver value and you can measure it in time and cost and quality and safety, those are the only four things that really matter, right? To everybody. And there are a few people that'll pay for perception of coolness but that's not where I'm focused. I'm like, is it better, faster, cheaper? And does it help people's lives that are either manufacturing or using the end product? Does it help them? Great. It's worth paying for. So there are some as well who will say, hey, we're going to make a video and you got sparks flying and it looks cool, and it does. It looks cool. It's super fun. That aspect of it is fun. But I try to remind people, it's only fun if you're actually making money with it and you got a business case that supports you and you're accelerating. It's no fun to pay for something that looks cool on a loan that's now you're not able to make the money on, and we want you to have value.
Right.
That's the only way this thing scales.
Right. Yeah, and I mean, I think it's worth noting that, because I operate in the manufacturing marketing space, that, most of the searches that we see come from, we really like when a manufacturer has a combination of skill sets, an unusual combination of skill sets. So whether that be a shop that can do welding and machining, like that's unusual. Not a lot of machine shops have welding capability. So there are companies out there I know have looked for welding and machine because they're looking to kind of consolidate their supply chain. Or if they're looking for a shop that can do the metal plating and the machining. So I think the ones that aren't advertising the machine maybe not from a cool video sparks flying standpoint, but from actually understanding what this is offering to the marketplace, whether, like you said, it be saving time, saving cost, improving quality. Those are the big things that matter in manufacturing. So if you can say that you have a superior capacity for that, it's going to get you more business if you talk about it in the right way.
Agreed. Yep, absolutely. And I probably answered a little bit for those who are maybe more captive machine shops that have a product, a very clear product offering.
Right.
Certainly, as you advertise from a subcontract capability perspective,
Yep.
hybrid manufacturing, I believe, will be a credit to you in whatever form you're doing it.
Yep.
And bear in mind that many people's definition of that is maybe narrower than what I think it should be
Right.
and will be.
Right. Well, I hope this podcast helps that goal a little bit. And I think you did a great job of explaining what this technology does and can do. And I like how we explored a lot of different applications for it. So I think this would be very interesting to a lot of shops out there. So thanks for the time to share. And I think what you're doing is awesome. I love to see your passion for manufacturing and 3D printing. At Manufacturing Insiders, our goal is really to share that peer-to-peer knowledge between manufacturing CEOs and service providers and really bring these new products to the forefront and hopefully increase adoption.
We certainly appreciate that. And anything that can elevate, my view is, post World War II, many of the leading economies of the world had their manufacturing capacity decimated. The US was the exception to that. And I believe that accounted for a large proportion of the prosperity we experienced for at least 50 plus years following that.
Right.
And I'm optimistic and very, bullish on trying to keep American manufacturing, its capacity, its flexibility, and its ability to do things in a less dangerous, dirty, right? There's so much around the kind of mindset of manufacturing that doesn't feel as desirable as it actually probably is.
Right.
And certainly not as advanced as it's very rapidly becoming.
Right.
So thank you for helping to build, North America and beyond in terms of the voice that you raised.
You're welcome. And thanks for coming on today, Jason. Great talking with you.